Okay, so we've talked about the forward transform, which is pretty simple to obtain as a series, and the inverse transform is not so easily obtainable. You need to get a contour integral around the region of convergence, and numerically it doesn't lead to any useful results. It doesn't reveal the true usefulness of the Z transforms. So the question is, instead of using this proper inverse transform, how can we proceed with rational transfer functions or rational Z transforms to obtain some properties of different signal source systems, or what these systems are, or what these signals are. So we can use different techniques. I'm just going to talk about two of these. The first is power series expansion. We would want to try to express the Z transform as x of z equals to, for all n, c sub n z to the power minus n. That is, in the way that we're obtaining the signal itself. Cn will be one value of the signal, because that's a direct Z transform, right? So let's give an example. So here's our example. X of z is 1 minus 1.5 z to the power minus 1 plus 0.5 z to the power minus 2 to the power minus 1. That is 1 over this. And we have a region of convergence, which tells us that the signal as is a causal signal. So this is causal. Okay, that is nice. So let us then proceed with what the simplest way of proceeding with such a problem is. And that is division. Kind of simple high school division. Or even, I don't know, elementary school division, if you want to call it that. So let's have a look. So we start with writing down the numerator numerator. It's not a polynomial anymore. It's one numerator polynomial here, and we would want to divide it by the denominator polynomial, which is 1 minus 1.5 z to the power minus 1 plus 0.5 z to the power minus 2. So this is really simple division. So how do we proceed with division? Let's have a look. The first term is 1, which means if you multiply our numerator polynomial by 1 and subtract it from the denominator polynomial, so let's just write plus here, and then we have minus 1 plus 1.5 z to the power minus 1 minus 0.5 z to the power minus 2. So we add these two together, which is going to give us 1.5 z to the power minus 1 minus 0.5 z to the power minus 2. Okay, so let's have a look at what we have then. We still have 1 as the first term, so we're going to multiply this by, 3 over 2 plus 3 over 2 z to the power minus 1, which is going to give us exactly so we are going to multiply this. So we're just going to add minus 1 over 5 z to the power minus 1 plus 9 over 4 z to the power minus 2 minus 3 over 4 z to the power minus 3, which will give us 7 over 4. There may be a little bit of a mistake in here, so please do let me know if there is any mistake so I can correct it later. So minus 2 minus 3 over 4 z to the power minus 3, etc., etc. So we can eventually find this series as having these coefficients plus 15 over 8. So this is just, simple division really. I'm not going to go ahead and solve it, etc. The actual values don't matter actually, but the method matters. So this can be done relatively easily. And this operation, as we shall see later on, is called deconvolution. So this operation is called deconvolution. You may remember me talking about convolution as a product of two polynomials. So that is, if you multiply two polynomials, you're convolving them, and if you're trying to separate them, so to speak, you're carrying out the exact opposite of that operation, which is called deconvolution. Okay, so another method is partial fraction expansion. So we would like to express the Z transform in terms of simpler terms, which are x sub q of Z, where AQ in this case is typically a real or a complex number. So let's write AQ is in many cases real, but it can be complex for some cases. Okay, so let's have a look at the general case where we have a rational expression for x of z. We can define two different types of functions. If the number of poles is greater than the number of zeros, then we have a proper function. If the number of poles is less than or equal to the number of zeros, then we have an improper function. So application of partial fraction expansion for these two cases is slightly different, and we're going to see that through two examples. Okay, so our first example, we're assuming that x of z is proper. What we do then is we just multiply the numerator and denominator by z to the power number of poles, z to the power n, which gives us two polynomials, the numerator and denominator polynomials, which have the highest order terms as z to the power n. Then we divide the numerator by z, which will give us a definitely proper polynomial. Obviously, we are assuming that n is greater than m, which means in the worst case scenario, we're going to have this term as being z to the power 0, which is 1. Okay, so this gives us, however, on the right-hand side, on the left-hand side, xz over z. So we would have to deal with it later, right? So let's have a look. Then we would like to express xz over z in terms of simpler polynomials, which look like this. So simpler z transforms, which look like this. And we would like to find out by partial fraction expansion what zq are and what aq are. If we have a multiple root, that is, if we have a root at z equals to 0.7, but we have two roots there, then we would have to deal with it in this way. We would have, for that specific root, we would have a term which has both zeroth order and first order terms. And we would have to calculate a sub qk for each repetition of that root. Okay, so let's not go into that. Let's give an example for a proper function that is, in the numerator we have -1 plus z to the power -1, and in the denominator we have 1 minus 1.1 z to the power -1 plus 0.18 z to the power -2, and we have a causal signal. Okay, so this is Z transform, and just by looking at the region of convergence being greater than some P, so outside the circle, which means we have a causal signal, which is good to know because we will use it. Okay, so let's try to work with this expression. So what do we do first? We multiply both the numerator and the denominator by z squared, right? So we end up with minus z squared minus 1, I'm sorry, z squared minus, z squared minus z over z squared minus 1.1 z plus 0.18. Okay, so then we have two polynomials of order 2. Now let's do our trick with x of z. So we divide both sides by z, which gives us minus z minus 1 over z squared minus 1.1 z plus 0.18. Okay, so how do we proceed then? We first need to find the roots of the denominator polynomial in order to express our expression in terms of simpler z transforms. So the roots of this denominator polynomial can be easily shown to be, again by using high school maths if you like, a1 equals to, z1 equals to z1 equals to 0.2 and z2 equals to 0.9. Okay, so this gives us the general form of the Z transform. So let's write it down. Okay, then x z over z is equal to minus z minus 1 over z minus 0.2 times z minus 0.9. Okay, so we would like to write this in a form which looks like this, minus a1 over z minus 0.2 plus a2 over z minus 0.9. And again, there might be some mistake with the numbers which I give you. I'm writing directly from my notes, which means if you find a problem with these numbers, please let me know so I can revise them. They should be correct. Last time I looked, they were correct anyway. So a1 is 8 over 7, and a2 is minus 1 over 7. Based on this, then x of z over z is equal to minus a1 over z minus 0.2, let me just write the actual number, minus 8 over 7 over z minus 0.2 plus, minus 1/7 over z minus 0.9. And if you want to work that out, so let me just save it and move things a little so that we have some more space, maybe. Okay, so I'm going to continue writing here. So let's write the z transform then of x. So x of z is equal to minus 1/7, 8z over z minus 0.2 minus 1 over minus z over z minus 0.9. And we can divide both the numerators and denominators by z, which is going to give us 1/7 minus 1/7, 8 over 1 minus 0.2 z to the power minus 1, minus 1/1 minus 0.9 z to the power minus 1. Now we know that this term comes from an exponential sequence, this first term, as well as the second term. So these two terms come from exponential signals. So this is eventually a combination of two exponential signals then, and we can write it as such. So then x of n is equal to minus 1/7 8 times 0.2 to the power n minus 0.9 to the power n u of n. U of n we do know because we have a causal sequence. So this is how you would proceed with a proper function, proper rational function. What happens if you have an improper function? So if you have an improper function like this, multiplying the numerator and the denominator by z squared is going to mean that we have indeed two polynomials for this specific case which have the same order. That means z squared minus z minus 1 over z squared minus 1.1 z plus 0.18, which is fantastic. However, we have an improper function. That means if you want to write it in a form which has the two poles in them, you're not going to be able to find those two terms, a1 and a2. So the way to proceed in this case is first carry out a division to eliminate the constant term and then carry on with what remains. That means we first write the numerator polynomial and then divide this by the denominator polynomial. We're only going to carry out the first step to find the remainder. So we have one of this within this, which means we're going to add minus z squared, okay, plus 1 minus 1z minus 0.18 which will give us what? 0.1z minus 1.18. Then we can write this expression x of z in this form. 1 plus 0.1z minus 1.18 over z squared minus 1.1 z plus 0.18. Then following this, we can express the second part, which is a proper function in terms of simpler form. So we would then go ahead and proceed by writing this a 1 over z minus 0.2. We have the same poles plus a2 over z minus 0.9, etc. And I don't really know if these two numbers are correct. I'm not going to work through these, but a2 happens to be something like 58 over 35. A1 happens to be minus 109 over 70, etc. The actual numbers don't matter too much. But this is how you would proceed. And yeah, the time domain expression can be obtained in the same way as in the previous example. Okay, so far so good. We have seen two ways to invert the Z transform. But one thing where it's very useful is responses of systems with fractional system functions. Because if you carry out this inversion, it's going to tell you about the impulse response of your system. So let us assume that we are inputting a signal x of z, which has a rational z transform n of z over q of z. We're inputting that signal as an input to the system with a transfer function h of z equals to b of z over a of z. And let's say h of z has the poles pk for all k from 1 to k, capital K, and xz has the poles q sub l for all l from 1 to capital L. So we have k poles for the system and l poles for the signal that we input to that. Now, something we would need to remember is if we have a signal x of n and we're convolving with an impulse response h of n in z domain via the convolution theorem, we have the z transform as the product of these two z transforms. Okay, so we can express y of z, which is the output of our system, as the product of h of z and x of z, and then we can separate this into two as terms which have the as simpler terms which represent the poles of the signal and poles of the system, so pk and ql. So this is obviously kind of looking at it from a higher level perhaps, but in practice that is how you could proceed with this. So let's write the output in time domain then. So y of n is equal to, for all k from 1 to n, a sub k. Now we have p sub k to the power n, this is exponential, right? U of n. And then plus, we have L poles coming from the signal So k from 1 to L this time, qk, and then q sub L to the power n u of n. Okay, we can now identify two different types of responses. The first response is a natural response of the system. So let's just define it as such. So this is the natural response. That is the response of the system if you do not even consider that you have x of z in place or an input in place. So this is the natural response. And then you have the forced response. So this is the forced response. Let's call it YFR for forced response. So why are we calling them these? Without, if you don't even feed any signal, or if you feed any signal, in fact, to our system, this natural response is going to stay the same because it's inherent to the system. So all poles, pk, come from the system itself. Whereas the second part comes, this set of, should have been k, the set of poles, this set of exponential signals, combination of exponentials, comes from the signal itself, the input signal itself, which means it can be different for a different type of a signal. So that is why we call it a forced response. We're forcing the system to provide this response in a way. So this can be considered also as transient and steady state responses. If you feed a sinusoidal signal to your system, or a steady state continuous periodic signal, for instance, to your system, then you're going to have that forced response. Otherwise, you're going to have the transient response. If you cut the input to your system, the way that your system is going to respond is its transient response. So let's define it as such then. If all the poles of our system are less than 1, as n goes to infinity, y natural response n is 0. So that is transient. So it's gonna wither away, so to speak. If qk is less than 1, as n goes to infinity, y forced response n is also going to be 0. However, if the signal is sinusoid, so if the signal is a sinusoid such that qk, any qk, is on the unit circle, then the system is going to provide the steady state response. So in this case, in the first case, we're talking about the transient response, and in the second case, we're talking about the steady state response. All right, so finally, we're going to discuss stability of a system. We can assess the stability of a system by its Z transform. It's one of the simplest ways to do that. As long as your Z transform converges, as long as you are in the region of convergence, you can analyze whether or not your system is stable. So for a system to be stable, its region of convergence should include the unit circle. Why is that? I mean, unit circle represents sinusoids, right? So we have e to the power j omega, b to the power j theta, whatever, which means we are dealing with unit amplitude, driving our system, for instance, by unit amplitude complex exponentials, which correspond to sinusoids, which have a fixed amplitude. So in order for our system to handle such sinusoids, its region of convergence should include the unit circle. If it does, then perfect. Your system will then be stable. So, assuming that we have a unit circle here, in both cases, we can have a region of convergence which has this form, for instance. So we have a region of convergence for a non-causal signal which includes the unit circle this way, or we may have a region of convergence which is outside a circle, so we have, for instance, a non-causal signal, a non-causal system. So these are just two examples. You may have a ring which contains the unit circle as well. So if we have a causal system and our system is stable, the Z transform, direct Z transform is given in this form. So we have a causal system which we want to be stable, and we have a region of convergence Z greater than P. We would have all poles inside the unit circle. If our system has poles, then all of the poles are inside the unit circle. But if we drive a system which has a pole on the unit circle, so we have a pole on the unit circle, it is going to produce unbounded output. So it's going to be critically stable, or it may act as an oscillator as such. If you excite it with an impulse and don't excite it anymore, if you just send it an impulse, it's going to start oscillating and it's going to create a sinusoid at that specific frequency which that specific pole corresponds to. Then it will be, if you like, critically stable. But if you feed it a constant, if you feed it something like a sinusoid, then it's going to diverge. The output is going to diverge, and its output is going to be unbounded. So, so much so for stability of a system. This concludes this week's material on Z transforms. Please do check Otto class. I provided some Python examples which you can play with. They're fun. They're on Binder, so you can just go to the website, go to mybinder.org, to the link that I provided you with, and play with the example there. But I strongly urge you to install Python and Jupyter so that you can play with the code on your own computer. That is going to give you perhaps more insight than what these videos can possibly provide you with. So it's going to give you the option to play with the code, play with different values, and see for yourself what happens to a signal, a system, when you change certain parameters. So thank you very much for listening, and see you next week in our next video.